So in the previous video we were looking at the norm on the vector space, well, the ring z root 2, and the norm n of x took x to x bar, where x bar is the reflection of x over the axis in the same way as in complex numbers. So this is square root of 2, 1, something. Maybe I did it the other way around by accident the other time, but it doesn't actually matter, I don't think. Actually, wait, it does matter. So wait, let me just double check. I know I did it correctly. It doesn't matter. Okay, so it had the square root of 2 is what's getting negatified, you know. So if this is a plus b square root of 2, this would be a plus minus b square root of 2. And if for nothing else, it's just so that when you multiply, you get the Pell equation. And we see that the Pell equation is really just asking for all x with norm equal to 1. So really, we've changed the Pell equation, which was about finding pairs of numbers with some property, into finding all the elements of this vector space that have norm 1. How does this make the problem any better? Well, first of all, we do know some things about the norm. For example, this xy, we can easily write it out as xy times xy bar. Okay, so at this point you might be wondering, okay, this x by bar, can we simplify it in any way? And the answer is yes, we can. And so first of all, let's actually write it out. X y bar. So xy bar, right, is the complement of xy. So let's just compute xy first. So so if we compute xy, then let's see. Oh, so we need to pick some values for x. So x is a plus b square root of 2, and y equals c plus d square root of 2, and we'll complement the whole thing. And we multiply this inside first, and then we'll take the complement of the whole thing. So from before, we know this a AC plus 2BD plus AD plus BC, yeah, square root of 2. And because of the complement, it just becomes minus. So we have AC plus 2BD minus AD minus BC plus square root of 2. And if you look at it for a little bit, you might actually notice that this is just the same as if you took the product without the bar, but with these two as minus symbols. So in fact, this is the same as a minus b square root of 2 times c minus d square root of 2. Okay, so why is this true? Well, the algebra says it's true, but what is the idea behind this? Well, it's because all we're doing is everywhere we're replacing the square root of 2 with minus square root of 2, right? Over here, what we did was we replaced the square root of 2 with minus square root of 2, and over here, well, once again, replacing square root of 2 with minus square root of 2 with square root of 2 or something. But the thing is, minus square root of 2 and square root of 2, they have the same properties, right? They satisfy the same polynomial. They satisfy the same, what do you call it? So, because by the definition of algebraic numbers, that they have to satisfy polynomial, and that polynomial is what we use to look at the structure of the algebraic number. So really, when we say square root of 2, we would just mean the number that satisfies x squared minus 2 equals 0. We don't mean anything else. We don't mean the ways fractional expansion for it or anything like that. We just mean the number that satisfies this equation. But this equation can be satisfied by both minus the square root of 2 or the square root of 2. So essentially these 2 points are just dependent on which one we choose, which of the solutions we choose. And so this is why we should expect that if the product works normally without these bars, right, when we switch everything to the other world, all the algebra should remain the same, simply because this is the only thing we care about, and that stays the same. Okay, okie dokie. But anyway, now what we can do is we can plug that in. N of x, y is x, y like that, in maybe brackets. And what we can do is we can shuffle the terms around. And we get x bar, y bar, and we have that n is n of x, n of y. That is, the norm is multiplicative, and so that is pretty useful, a pretty useful result. And let's see, so if we can't see right away why it's a pretty useful result, let's put it this way. We have that the norm here is 1, norm of x is 1, right? That's what we want. And actually we'll see why it's useful in the next video.